Hi, my name is Shanaz. In this lecture, we'll discuss metrizable spaces and we'll study some properties of metrizable spaces. But first, we'll define metrizable space. So we have this definition. So let us consider a topological space X. So this X is our given space. So then we call this X to be metrizable. Then X is called metrizable if there exists a metric on X. So if there exists a metric on X that induces the topology of X. In last lecture, we have seen how a metric on a space induces a topology on that space. So, for example, if we consider a metric space, then it is metrizable. So every metric space is metrizable since the metric induces the metric topology on it. Every metric space is metrizable since the metric induces the metric topology. So let us call this first example. We have another example. So let us take X to be a space together with discrete topology. Then X is also metrizable since there exists the discrete metric on X that induces the topology on X, same as the discrete topology. So let X be any set, let X be any set together with discrete topology. Then this X is metrizable. Then X is metrizable since the discrete metric on X induces the topology same as the discrete topology. Same as the discrete topology. In the last lecture, we have seen how a discrete metric induces the discrete topology. Now we have this property first. Let us discuss this property via theorem. So let f from x to y. So let f from x to y, where these x and y are metrizable metric spaces, should be a function where x and y are metrizable with matrix say. So with matrix say dx and dy respectively. Then the continuity of f is equivalent to, so the continuity of f is equivalent to the requirement that given any epsilon positive, there exists a delta positive such that whenever the distance between the points x and y is less than delta, this should imply the distance between f of x and f of y is less than epsilon. So if we have the space x here and we have the space y here, so since we have the metric dx on this space and the metric dy on the space, and we have the function f here, so if we choose 2 points here, say x and y, so whenever the distance between these 2 points, I mean this distance, so this is the distance dxy, but this is with respect to the metric dx, and we have their image here. So this is f of x, this is f of y. So this is a distance and dy y fx fy. So whenever this distance is less than delta, this distance has to be less than epsilon. So that is what we mean by for any epsilon positive there is this delta positive. So let us prove this. So uh, suppose f from x to y is continuous. Now since f is continuous, so it pulls back open sets to open sets. Therefore, f pulls back open sets to open sets. So hence, if we choose an open set in y, so hence given x and epsilon greater than 0, this set, so this set, I mean this set f inverse of b dy fx epsilon. So this is the ball, so if this is the space y and we have a point f of x here, then we pick this ball. So this is the ball centered at fx and radius epsilon. So this ball is induced by the metric dx. So we'll look at, now this ball is an open set in y and this f is continuous, so this f pulls back this open ball to open ball, so this inverse image of this ball, this is an open set in x. So this, then the set is open in x, and of course it contains the point x, and because this ball contains f of x, so its inverse image will be an open set which contain the point x and contains the point x. Since this, the reason is that since this ball is open, since the ball centered at fx and radius epsilon is open in y and contains the point fx. Now uh, if this is the case, then I mean if f inverse of this ball is open, then this set is neighborhood of each of its points. So in particular this set will be a neighborhood of x because x sits there. So therefore f inverse of the open ball fx epsilon is a neighborhood. Let us call, for a shorthand, we write this neighborhood by nbd. So this is a neighborhood of x, and hence there is a delta ball centered at x such that the delta ball is contained here. So and hence there exists a delta ball, say b dx x delta. I mean this ball is centered at x and radius delta. So this is a ball b x delta. So this is induced by the metric dx. So so this ball is centered at x such that this ball is contained in this set. The reason is that this set is neighborhood of x such that this ball is contained uh, in this open set f inverse b dy fx epsilon. So that means if we choose a point, say y, in this set, then f of y will be in this set. So therefore if y belongs to b dx x delta, then it is f image, and because y being an element of this set and this set is contained here, so that means f of y has to be an element of this set. So this means if distance between x and y is less than delta, then distance between f of x and f of y is less than delta. That means we pick y here. So if y is there, then f of y is here. Now if y is here, that means, so this implies that uh, if distance between, now we pick y in this open ball, that means the distance from the center x to y has to be less than delta. So if this is less than delta, then so this is the dx, then the distance between the center and this point, so it has to be less than epsilon. So this proves one direction. Now to prove other direction, we'll proceed as follows. Now conversely, suppose that this epsilon delta condition is satisfied. Suppose so we assume that this condition is satisfied. I mean, we assume here that for any epsilon positive, there always exists a delta positive, such that whenever this is less than delta, we have this thing over here less than epsilon. So we call this epsilon delta condition. So we will prove that f is continuous. Now to prove f is continuous, we'll prove f pulls back open sets to open sets. So we wish to prove f from x to y is continuous. That is what we want to prove. That means we have to prove that is f pulls back open sets to open sets. So that means we'll pick an open set in y. We'll prove the inverse image of that set is open in x. So let v be an open set in y, and we prove f inverse v is open in x. Now to prove this f inverse v is open in x, we have to show it is neighborhood of each of its points. So let us pick any point in this set. So let x is in the inverse image of v. So if this is the case, then f of x is an element of v, because x is in this set, so f of x has to be in v. That is the definition of this set. Now this v is given to be open, uh, and fx is a point there. That means v is a neighborhood of f of x. So hence there is an epsilon ball centered at f of x, which is contained in V. So and hence there exists an epsilon ball, say b dy fx epsilon. So this ball is centered at fx, such that uh, the image of this ball such that such that this ball is contained in V, such that b dy fx epsilon is contained in V. And the reason for this is that V is open. So since V is open, so by epsilon delta condition, so for this epsilon there is a delta positive. So by epsilon delta condition, uh, there exists a delta ball, say b dx x delta. So this ball is centered at x and radius delta. So centered at x, such that it is f image is contained in such that f of b dx x delta. So this is contained in the ball centered at f of x and radius epsilon. So so this shows that so if this is the case, then this ball is contained in the inverse image of this set. So this shows that the ball centered at x and radius delta is contained in the inverse image, because f image of this ball is here. So this ball must be contained in the inverse image of this set under f. So this is f inverse of b dy fx epsilon. But this uh, is an open set in V. So this set is contained in V. That means what we proved here, we proved V is actually a neighborhood of X, and that proves the openness of the set F inverse V. Sorry, this is not V. This is F inverse V, because this ball over here, this is inside V. So, so since the ball centered at x and radius delta contains x, and is contained in f inverse V. So f inverse V is a neighborhood of x, and hence f inverse V is open. This proves the continuity of f. Now there is one more property that we call the sequence lemma. So this is also called as the sequence lemma. So this lemma states that, so let X be a topological space so if there is a sequence of points of, so let X be a topological space, and suppose this A is a subset of X. So let, I mean, if there is a sequence of, if there's a sequence, say xn of points of A converging to X, such that xn converges to X, then this X is in the closure of A, and the converse is true only if the space is metrizable. I mean, if we have a sequence xn of pointers, I mean, if X is in the closure of A, then there is a sequence of points of A converging to X. So that is, it is converse, and this converse is only true when this space X is metrizable. So that is, uh, the converse is true uh, if X is metrizable. So let us prove this. So one direction is, I mean, if we prove this direction, this is trivial, this is uh, easy to prove. So for this, let us take a sequence of points of A. So let xn be a sequence of points of A such that this xn, this converges to X. Now, if this is the case, then if we pick any neighborhood, say u of X, that neighborhood contains all but finitely many terms of this sequence. So then every neighborhood, say u of X, uh, contains a point of A. This contains a point of A. So this is true for any neighborhood of X. That means this X is actually the accumulation point of A. So, and hence X has to be either an element of A, or X has to be a limit point. That means this X is in the closure of A. So this is trivial. Now conversely, suppose X is a metrizable space. So conversely, let X be a metrizable space. So that means, I mean, what we do, we choose X to be metrizable space, and we pick some point in the closure of A. And what we had to prove? We had to prove there is a sequence of points of A which converges to this point X here. Now, since this X is metrizable, there has to be some metric D which induces and the topology of X. So let us call that metric to be D. So let D be a metric that induces the topology of X, because we choose X to be metrizable. Now for each, so the situation here is like this. So this is the space. So we have sequence of points, and here we have the set A, and in set uh, I mean this is, let us call this A closure here, and we pick a point X here. So we have to prove there is a sequence of points that converges to X. Now since X is an A closure, that means any neighborhood U of X contains a point of A. Uh, in particular, any open ball centered at X is also a neighborhood of X. So that means any open ball centered at X must contain a point of the sequence. So for each positive integer n, take the neighborhood, take the neighborhood, the ball centered at X and radius 1 by n of X. So this is the neighborhood of this ball. Now this X is given to be a point of A closure. That means this neighborhood must contain a point of A. So since X is in the closure of A, the intersection of this open ball with A has to be non-empty. So we pick some point there. So let uh, X n be a point in this open ball, I mean in this intersection. Huh. So this is true for any positive integer n. I mean if we pick the positive integer m, then we have an open ball centered at X and radius 1 over m, such that this open ball contains a point xm of this set A closure. This is not A closure, is A here. Now uh, for each positive integer, since we have these pointers, we collect all these points and we get a sequence of pointers which sit inside A, because all these points are in these open balls as well as in A. So let uh, let us now consider the sequence xn. We take all these points, and since for each positive integer n we have a point of A, so we collect all these points and we get this sequence. Now we claim that this sequence converges to X. So we claim that this xn converges to X. Now to prove our claim, what we do, we will show that there is an open neighborhood u of x that contains all but finitely many terms of this sequence, and that will prove our claim. So note that any epsilon ball, say be the x epsilon, which is centered at x, contains not epsilon ball. I mean, note that any open set U containing X contains an epsilon ball centered at X. I mean, this epsilon ball BD X epsilon centered at X, centered at X. The reason is that this X is in the closure of A. Now, if we choose N, so if we choose M belongs to the natural numbers, so that 1 over M is less than epsilon, then U contains U contains xn for all n bigger or equal to m. So this contains xn for all bigger or equal to m. Since the reason is that, so since xm is in the ball centered at x and radius 1 over m. So one can note here, if xm is in this set, and if 1 over m is less than epsilon, then this xm is in this ball as well, because for 1 over m less than epsilon, this ball lies over here. So then u contains uh, xm for all. So I have wrote this down here. So in this open ball over here, this is contained in BD x epsilon, because 1 over m is less than epsilon. So these two balls, they are centered at the same point x, and this ball over here, this has a radius less than the radius of this ball. So this ball over here sits in this ball. So this is true for all m bigger or equal to n. So that means if u contains this ball over here, and this ball contains all the terms of sequence but finitely many, so this means that this sequence xn converges to x. So this shows that xn is converging to x. Now let us prove one more property over here. So let us take a function. So let f from x to y be a function. So if the function f is continuous, so if f is continuous, then for every then for every convergence sequence, say xn, where this xn converges to x, the sequence, so we have this sequence. Let us write this down. And then this is convergent. So this is the convergent sequence in x, where xn converges to x. So this is the sequence in this set. What we claim? We claim this sequence of the images of the pointers of this sequence. I mean f of xn. Then this sequence f of x and this converges to f of x. And um, once more, the converse is true only. I mean, the converse is true if x is metrizable, and the converse is true if x is metrizable. So let us prove this. So let us take a function. So let f from x to y. So what we have to prove? We have the space x here and the space y here. So we have a sequence of pointers. Say uh, we have a sequence of pointers. Say xn. So this is x1, this is x2, so on, and this is a point x. I mean, this sequence converges to x, and we have the another sequence which is the images of these points f of x1, f of x2. So we claim this sequence converges to f of x. So let us take this to be a function. So I mean, let us proceed this way. So assume that f from x to y is continuous. Let us take a sequence. So let xn be a sequence in x such that this xn converges to x. So we wish to prove the sequence f of xn converges to f of x. Now to prove this thing over here, we have to prove any neighborhood v of fx contains all but finite many terms of this sequence. I mean the sequence f of x n. So let us pick any neighborhood v of f of x and y. So let v be any neighborhood of f of x in y. So if this is the case, then f being continuous, it is inverse image is continuous. Sorry, open. So then f inverse v is open in x, and hence f inverse v is a neighborhood of x in x, is a neighborhood of x in x. The reason is that f inverse v is open. So but since x n converges to x, and this f inverse v, this is the neighborhood of x, so that means this f inverse v contains all but finitely many terms of the sequence of x. So hence, I mean, since this converges to x, this set f inverse v contains all but finitely many terms of the sequence xn. So hence, so if this is the case, that means there is a stage after which all the terms of the sequence lie in the open set f inverse v. So hence there exists a natural number m such that xm belongs to f inverse v for all whenever we surpass this stage, for all m bigger sorry, for all, this is not m here, this is n here, for all n bigger or equal to m. So this implies that so if this is the case, then by definition of this set over here, f of xn belongs to v for all n bigger or equal to m. So what we proved here, we proved the open set v, which is neighborhood of f of x, and this which is the neighborhood of f of x. This neighborhood v contains all the terms of the sequence after this stage. So this proves that this open set v contains the limit point of this sequence, which is in this case the point f of x. So this shows that f of xn, this converges to f of x. The reason is that this v is neighborhood of f of x. Now to prove it is converse, we assume that this space is metrizable. Now to prove the converse, assume that for any sequence xn converging to x, the sequence f of sequence f of xn converges to f of x. So we wish to prove this f is continuous. So we wish to prove f is continuous. So it suffices to prove that f take is the points which are close to a to the points which are close to f of a. So it suffices to prove uh, f of a closure is contained in f of a, this whole closure for any subset a of x. I mean, this is what we mean by continuity. I mean, um the continuous functions preserves the closeness. Now this means f takes all the points in a which are close to a to the points which are close to f of a. So now to prove this, we pick any point in the closure of a. So let x is in the closure of a. Now using previous lemma, since x is in the closure of a, then there is a sequence of pointers of a which converges to x. So let x belongs to a closure. So since uh, x is metrizable, there exists a sequence xn of pointers of a such that this xn converges to x. So here we are using the previous lemma. So by hypothesis, since this converges to x, then this sequence f of xn converges to f of x. So by hypothesis, f of xn converges to f of x. Now, since this sequence x and this is the sequence of points of a, we have, so since xn belongs to a for all n, f of xn belongs to f of a for all n. Now we are again using the previous lemma. So since this sequence is the sequence of points of a and it converges to the point f of x, that means this f of uh, x has to be a point of f of a whole closure. So then by previous lemma, f of x belongs to the f of a whole closure. So we chose this x to be a point of a closure and we show that it is images in the f of a closure. So this shows that f of a closure is contained in f of a whole closure. This proves the continuity of f.